Exercise 46. So a function defined Rn, Cartesian product is Rn to R is inner product if and only if evaluate at two vectors of Rn. So let's say n by 1 column matrix x and y equals the transpose of x, matrix multiplication with a matrix A, matrix multiplication with matrix column matrix y, n by 1 column matrix, where this A is a symmetric matrix with eigenvalue strictly positive. So positive definite as a matrix. Solution. So first let me put a remark. So recall that the dot product of two vectors on Rn, this is just x transpose y. Matrix multiplication, which means corresponds to A equals identity, right? In particular, this tells you that dot product is, in particular example, inner product, of course, and so in that precise example, you have A symmetric and all the eigenvalues strictly positive. So let's first show that if E is an inner product, then it is of the form xday. So let's still denote by EI, the standard basis of Rn, and then this x equals x1 xn, n by 1 column matrix, and then compute their inner product. Just by the x rows of inner product, this would be use the linearity. This would be again summation of xi, yj, ei, ej. So this is not the dot product, so we don't know those standard basis is orthonormal, something like that, we don't know. Just have to keep record of all those ij. And so if you define this to be your aij, this is of the form xi, aij, yj. In particular, let's remark this is exactly the same as transpose of x, a, and y, where define A to be the matrix whose ij entry is aij. So this just follows from direct computation. Maybe there are some small techniques, but basically this is just computation, I think. So x transpose of x1, x2, xn. So let me write it more. So let me first write A1 into the column matrix, the column vectors, sorry, of A, and then, so this would be, so maybe let's look at this. So this tells you that actually you have, so this is, you think of it 1 by n, n by 1, so this would be 1 by 1, 1 by 1, this 1 by 1 is y1, A1, or even this A1 Y1. Think of it, this is like scalar multiplication. Y1 multiply into every entries of this A1. So A1 is basically A1 1, A2 1, AN 1. Right, so if you write multiply inside it, what you got would be A1 1 Y1, A2 1 Y1. So you see exactly find AN 1 Y1. Exactly Y1 appears on all those A something 1. Because what we want is the index Y corresponds to the second index of A, right? Just fit into that. Plus A2 Y2. So this is just a real number, 1 by 1 matrix if you want. Right, and then what is this multiplication? This multiplication is just again like scalar multiplication. So maybe let me put like this. It will give you one by n. Sorry, so this would not be 1 by n. This would be this is 1 by 1, 1 by 1, got 1 by 1, and then this is think of it as a row vector and then you have to multiply into it, right? Yeah, sorry, of course this is not a real number, so this is again, as we see, this is finally just n by 1 column matrix, so 1 by n by 1 again, you multiply into it, so we'll give you just x1 so it's better to write one more step to make this more realizable. Multiply with this is a one two y2 a 1 n y n. Right, do the same, and when you do the multiplication, this is like this, and so you have x1 a1 1 y1 plus x1 a1 2 y2. Exactly, x1 goes to all those left hand side of a1 something, and then plus x2 goes to all those a2 something. As you could imagine. So finally, x a and y. Okay, another way, so just computation, but another way would be let's just keep the order. Xn transpose, and then a, and then y. So namely this would, so if you first do this, this would be first row first column, first row second column, and then again let me write denote the column vectors like this for a, and then this would be just actually dot product of, or let me write one more step, this is X transpose as a matrix. Multiplication with the first column, right? And then multiplication as matrix multiplication the second column. And then here we have y. This is also the same as dot product of x with a1 dot product with a2. And then, so this is a 1 by n matrix. This is an n by 1. So finally, it's just x, the product, 1 and then y1, dot product a2, y2, dot product an, yn. This is a real number, and the multiplication by real number. Let's look precisely what it is. This is actually, again, we go back to here. So it's stupid to maybe to use translate into dot product. It's not necessary, but anyway, let's write down. So x1 a11 plus x2 a21 x3 a31, etc. So again, you see, the good thing is that, and then you multiply y1. Y1 is always on the right side, right hand side of a something 1, right? And so here again it's x1 a12 y2 plus x1 x2 a22 y2, etc. x and a n and y. So anyway, it gives you the same result. So which means you could translate this inner product of x and y using matrix multiplication, where you put this a, just the inner product of your standard basis EIJ. And now what do we have to do? We have to check that this a is symmetric and positive definite. Positive definite. First, the symmetry is easy because aij equals ei inner product with ej, which by axiom of inner product, which must be symmetric with respect to the position, and so this is also aji, so it's symmetric. Secondly, let's check its positive definite, which means all the eigenvalues are positive for this matrix A. And because this is a symmetric matrix from linear algebra, we know that it has n eigenvalues counting multiplicity. So in general, if we allowed complex eigenvalues, then always it will be, if you're n by n, you have n eigenvalues counting multiplicity. But for real entry matrix, it's not necessarily. You could have even matrix that has no eigenvalues, simply because you possibly cannot solve characteristic polynomial in real numbers, right? Just imagine, for example, let's say 0 0 minus 1 0, right? If this is your matrix, of course I'm not giving an example of symmetric, because symmetric we have a result that they always have counting multiplicity and eigenvalues. Then this gives you characteristic polynomial at this matrix, the determinant would be lambda squared plus 1. And so you have no real eigenvalues, while you have plus minus I as complex eigenvalues. So the two eigenvalues corresponding to dimension or size of this matrix is 2 by 2, right? Okay, so good thing for symmetric, we know that it always have n eigenvalues counting multiplicities. Let's say lambda 1, lambda 2, lambda n, which means possibly they can repeat. And the corresponding eigenvalues as say v1, v2, vn, the corresponding eigen vectors, sorry. And so when we see eigenvectors, of course, which means they are not 0. Because by our definition of eigenvalues, which means that eigenvalue is that when a x equals lambda x has non-zero solution x, then a lambda is called eigenvalue. Otherwise, 0 is eigenvalue. If you don't require this, have non-zero solution, then 0 is always a solution. And so it is otherwise telling you that any real number is eigenvalue with at least eigenvector 0. That's stupid. And so by the definition of eigenvalue, of course, we require that each eigenvalue has non-zero eigenvectors corresponding. So now notice that with this chosen or fixed eigenvectors, if we compute in particular this inner product of vi with itself, what we got is vi is vi transpose lambda I vi, and so scalar multiplication gives you vi transpose times vi matrix multiplication, but this is also the dot product of these two vectors, and so this is non-zero and this is bigger than 0. And again, this is inner product, which by the axiom should always be bigger than 0, and it is 0 only when this vector is 0, and so this tells you this is also 0, which forces all these lambda I to be bigger than 0. That's what we want to prove. Now let's prove the second direction. We want to show that if we define our inner product to be x transpose a y with a satisfying symmetry and positive definite, then this is an inner product, which means satisfies all the axioms. Okay, so recall what are those axioms. Firstly, xy equals yx. Okay, and just very quickly we could check this because x transpose a y corresponding to the left hand side, but this is a real number, right? Of course, it equals its transpose. The transpose becomes y transpose a transpose, but a transpose is a because a is symmetric, and then x. But this exactly corresponds to the right hand side, and so this is true in our case. Second thing to check, x it is linear, right? We have to check that x plus y, z equals x z plus yz, But then this is very directly. What is also directly scalar multiplication is preserved. Okay, so what is left to check is this bigger or equal than 0 and equals 0 if and only if x equals 0 vector. Right, this is the only one left to check. This is easy and directly just from the definition, you just check it. Okay, so let's check that. Of course, here we would use A is positive definite. Okay, but let's recall also that. Let me put in some exercise. So if A is symmetric, then, I mean real symmetric, of course, then there exists invertible matrix P such that P inverse equals P transpose such that AX instead of PDP inverse, you could now write PDP transpose. Of course, first is PDP inverse, which means A is diagonalizable. So this is famous result. We know that real symmetric matrices are diagonalizable, and moreover, it's not only diagonalizable, you could also write it into the form PDP transposes, but it's just because you recall how you construct your diagonalization, the P is chosen to be those engine vectors, right? This is telling you that some way you could choose your engine vectors such that P equals identity, right? And this is basically saying this is what columns are orthonormal bases, orthonormal vectors. And so you have this, which means for symmetric matrix, you could find your engine vector in your engine spaces. You choose linearly independent vectors and modify them to orthonormal vectors, and then you have this kind of more stronger diagonalization result. And so let's say with this, what can we see? And we know, of course, by assumption, all those lambda I or those on the mid diagonals are positive. So which means I say P is V1, V2, Vn. The corresponding diagonal matrix D would be lambda 1, lambda 2, lambda. Right. So now let's just compute for any x this is, by definition, transpose AX, but also let's write it using this diagonalization and then rewrite it as just notice this transpose to each other. So let's write transpose and then again P transpose X. If I just simply denote this by Y, I could write it as Y dy transpose, right? But then further notice so this is similar as computation we had done before, right? If you recall, we have done this computation. This gives you finally just xi, ai, j, yj, if you remember. And so here it tells you that. So basically, xi and x, this d is diagonal, so we only have those of the main diagonal. And on both sides, it will correspond to xi and yi, but xi equals yi. In this case, it will be just right. So this is just 1I squared lambda I, which means I'm denoting this. I'm supposing this is and so this is bigger or equal than 0, and this equals 0 if and only if all the way I equals 0, if and only if so this p-tx equals 0 if and only if p is invertible, x equals 0. And so we prove this is satisfied the last condition. Okay, let's come back here. One more remark. So, of course, you have this pt equals p inverse. I mean, to have this matrix whose column vectors are at the same time engine vectors, independent engine vectors, and also normal. This does not work in general. You cannot just say I'm using Gram-Schmidt process normalization and get whatever linear independent engine vectors into also normal one. That doesn't work because when you do the Gram-Schmidt procedure and also normalization, so basically the procedure Gram-Schmidt procedure, you keep the same span and turn this into another basis that is orthogonal, but you never guarantee that after your Gram-Schmidt procedure there's still the engine vectors, right? Because basically you keep your first one, and then the second one will be a linear combination of your previous first engine vector and second engine vector, and you don't know, they will again be engine vector with some engine value. But this works for symmetric one is because, so for symmetric matrix, the engine vectors corresponding to different engine values, they are orthogonal automatically. That could be also think of a sub exercise. That's why it works.